On the morning of June 19, 1944, Vice Admiral Jisaburo Ozawa stood in the flag plot of the aircraft carrier Taiho, studying reconnaissance reports that made no mathematical sense. His staff had compiled American carrier strength assessments from submarine sightings, radio intercepts, and aerial reconnaissance over the past 6 months. The numbers defied everything Ozawa understood about naval construction and industrial capacity. 15 American fleet carriers were operating in the Central Pacific. 15. Intelligence reports identified them by name: Essex, Yorktown, Intrepid, Hornet, Franklin, Ticonderoga, Bunker Hill, Wasp, Lexington, Hancock, Bennington, and more arriving each month. The Americans had commissioned one new fleet carrier every 6 weeks for the past 2 years. Japan had commissioned one fleet carrier, Taiho, in the same period. One carrier in 24 months, while America launched 17. The ship beneath Ozawa's feet represented 32 months of construction, consumed 16,000 tons of steel, and embodied Japan's entire remaining hope for carrier supremacy. Taiho displaced 29,300 tons fully loaded, carried 75 aircraft, and incorporated armored flight deck protection that no American carrier possessed. She was supposed to be the answer to America's numerical advantage: superior design, defeating crude mass production, quality overwhelming quantity. Ozawa knew it was a lie. The battle would begin in hours, and mathematics had already determined the outcome. 9 Japanese carriers would face 15 American carriers. 450 Japanese aircraft would engage 950 American aircraft. Pilots with an average of 100 flight hours would fight aviators with 500 combat hours. The Imperial Japanese Navy was sailing toward annihilation, and everyone in the flag plot understood this truth, even if no one spoke it aloud. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The question that consumed Ozawa's thoughts during the night before battle was deceptively simple. How did American shipyards accomplish what seemed physically impossible? Japan had spent 20 years developing the finest carrier force in the world. Japanese naval architects understood carrier design better than any nation. Japanese pilots were trained to standards that produced the most skilled aviators in any navy. Japanese carriers had struck Pearl Harbor with devastating effect, demonstrating tactical and operational superiority that shocked the world. Yet somehow, in less time than Japan required to build one Taiho, American shipyards were launching new carriers at rates that suggested industrial capacity of a scale Japan had never imagined. The Americans weren't just building more carriers, they were building them twice as fast using construction techniques that violated every principle of traditional shipbuilding. The story began not with admirals or naval architects, but with a dam builder named Henry Kaiser, who had never constructed a ship in his life before 1941. Kaiser was a civil engineer who specialized in massive concrete projects. He had built the Hoover Dam, the Bonneville Dam, projects that required moving mountains of earth and coordinating thousands of workers across years of construction. When the United States Maritime Commission needed cargo ships in 1941, they needed thousands of them to carry supplies across both oceans. Traditional shipyards said cargo ship construction required 6 months from keel laying to delivery. That was normal. That was how shipbuilding had always worked. You started with the keel, built upward one section at a time, riveted steel plates together with teams of skilled workers, installed engines and machinery, launched the hull, then spent additional months completing interior spaces. 6 months per ship multiplied by 2,000 ships needed meant impossible construction timelines. Kaiser examined the problem with an engineer's perspective rather than a shipbuilder's tradition. He didn't see ships. He saw steel structures that could be broken down into components, prefabricated in separate facilities, then assembled at the shipyard like building blocks. Instead of constructing ships from the bottom up one piece at a time, Kaiser proposed building ships from pre-manufactured sections that could be welded together rapidly. Traditional shipbuilders said it was impossible. Riveting was proven technology with centuries of successful application. Welding was risky. Welded seams could develop cracks that would propagate through the structure and break a ship in half. Kaiser said he would accept the risk because speed mattered more than perfection in wartime. He built 4 shipyards on San Francisco Bay in Richmond, California. He hired workers from across the country, most of whom had never seen a ship before. Many were women who had been excluded from industrial work. Many were African Americans who traditional shipyards refused to employ. Kaiser didn't care about experience or tradition. He cared about organization and systematic production. Kaiser divided ship construction into modules. Each module was built in a separate prefabrication shop. Deck sections, bulkheads, engine rooms, superstructures, everything broken down into pieces that could be manufactured by workers who only needed to know how to weld that specific component. The modules were built in whatever orientation made welding easiest, often on their sides or upside down. Massive cranes moved completed modules to the slipway where they were lowered into position and welded together. The first Liberty ship Kaiser built required 196 days from keel laying to delivery. The 10th ship took 45 days. By 1943, Kaiser's yards were completing Liberty ships in an average of 42 days. The record was 4 days, 15 hours, and 29 minutes for the SS Robert E. Peary, built in November 1942 as a demonstration of what systematic production could achieve. 4 days to build a 10,000-ton cargo ship. Traditional shipbuilders had said 6 months was the minimum possible time. Kaiser proved that modular construction, combined with welding technology, could revolutionize an industry that had remained essentially unchanged for centuries. The technique worked for simple cargo ships. The question was whether it could work for complex warships like aircraft carriers. Kaiser proposed converting his methods to escort carrier production, small carriers built on merchant ship hulls designed for convoy protection rather than fleet actions. The Navy was deeply skeptical. Carriers were extraordinarily complex vessels requiring specialized equipment, trained workers, and years of accumulated expertise. Kaiser said to give him a contract, and he would prove modular construction worked for carriers just as it worked for cargo ships. His Vancouver, Washington shipyard laid the keel for the escort carrier Casablanca on November 3, 1942. The ship was launched on April 5, 1943, and commissioned on July 8, 1943, 8 months from keel to operational carrier. The Navy ordered 50 Casablanca-class escort carriers. Kaiser delivered 50 carriers in 14 months, 1 carrier every 8 days on average. When Japanese naval staff in Tokyo received intelligence reports about American escort carrier production, they assumed the reports contained errors. 1 carrier every 8 days was physically impossible. It violated every principle of naval construction they understood. But the reports kept arriving, confirmed by submarine reconnaissance, aerial photography, and radio intercepts. American carrier task forces were appearing in the Pacific with numbers that made no tactical sense. 12 carriers, 15 carriers, 18 carriers operating as a single task force. Japan's entire carrier strength was 9 ships total. The Americans were deploying individual task forces larger than Japan's entire carrier fleet. The escort carriers were just the beginning. The real revolution was happening at yards building fleet carriers using techniques adapted from Kaiser's cargo ship methods. Newport News Shipbuilding in Virginia had been constructing carriers since the 1930s. They understood traditional carrier construction. They knew it required years of careful work by highly skilled craftsmen. But they learned from Kaiser's modular approach and began applying prefabrication techniques to fleet carrier construction. They started building carrier components in separate facilities before the keel was even laid. Hull sections, hangar decks, flight decks, island, superstructures, all manufactured in specialized shops, then moved to the slipway for final assembly. They replaced riveting with welding wherever possible. Welding was faster, required less skilled labor, and created lighter structures with greater strength. They standardized every design element. Every Essex-class carrier used identical plans, identical components, identical equipment. Workers learned to build one module, then built dozens of identical modules using the same techniques. They streamlined construction sequences so that multiple sections were built simultaneously in different locations, rather than waiting for one section to be completed before starting the next. The results were extraordinary. USS Essex, the lead ship of her class, was laid down on April 28, 1941. She was launched on July 31, 1942, and commissioned on December 31, 1942, 20 months from keel laying to operational carrier. That wasn't exceptional. That became the standard construction time for Essex-class carriers. USS Franklin, built at Newport News, went from keel laying to commissioning in 13 months. Several other Essex-class carriers were completed in 14 to 16 months. The average construction time was 18 months compared to 44 months for Japanese fleet carriers. American shipyards were building fleet carriers more than twice as fast as Japanese shipyards, and they were building many more of them simultaneously. By the time Taiho was commissioned in March 1944 after 32 months of construction, the Americans had 17 Essex-class carriers, either in service or under construction. The Japanese tried desperately to adapt. They ordered 14 Unryu-class carriers, smaller and simpler than Taiho, designed for accelerated mass production. The Unryu class was based on the proven Hiryu design, with modernization but using standard components. They displaced 17,150 tons, carried 65 aircraft, and could make 34 knots. They were supposed to be Japan's answer to the Essex class, demonstrating that Japan could also achieve mass production. 3 were completed. Unryu commissioned on August 6, 1944. Amagi commissioned on August 10. Katsuragi commissioned on October 15. 3 carriers within 10 weeks seemed like progress. Japan appeared to be accelerating carrier production to match American rates, but during those same 10 weeks, the Americans commissioned 9 Essex-class carriers. For every Japanese carrier that entered service, 3 American carriers joined the fleet. Japan wasn't catching up. The gap was widening with every month that passed. Worse than the production gap was the resource crisis strangling Japanese construction. Building a carrier requires enormous quantities of steel. An Essex-class carrier contained approximately 27,000 tons of steel plate, structural steel, and armor plate. The United States produced 60 million tons of steel in 1943 and 80 million tons in 1944. Japan produced 8.4 million tons in 1943 and 6 million tons in 1944. The American steel industry alone was producing 10 times more steel than Japan's entire industrial capacity. That steel gap rippled through every aspect of naval construction like a tsunami drowning Japanese shipyards. American yards had abundant steel. They could build hulls, armor, machinery, everything they needed. If a section was damaged or built incorrectly, they simply scrapped it and manufactured a new one. Waste was acceptable because steel was plentiful. Japanese shipyards rationed every ton of steel like gold dust. Every plate was precious. Mistakes couldn't be scrapped. They had to be cut apart and reworked. Construction slowed because workers spent time repairing errors instead of moving forward to new sections. The steel shortage forced compromises that degraded combat capability. 2 of the Unryu-class carriers, Katsuragi and Aso, were built with destroyer engines instead of proper fleet carrier turbines because turbine manufacturers couldn't produce carrier power plants fast enough. Those carriers could only make 25 knots instead of 34 knots. Slower carriers meant reduced tactical flexibility, reduced ability to evade attacks, reduced ability to close with enemy forces or retreat from danger. The Americans faced no such compromises. Every Essex-class carrier received identical propulsion systems, producing 150,000 shaft horsepower and 33 knots maximum speed. No exceptions, no substitutions, no degraded capability. The gap extended to machine tools. American shipyards had thousands of modern lathes, drill presses, milling machines, all powered and capable of precision work at high speed. Japanese shipyards rationed machine tools. Many were old, worn out, breaking down frequently. Replacement parts were scarce because machine tool production was prioritized for aircraft and tank manufacturing. Shipyard production slowed because workers waited for repairs while machinery sat idle. The gap extended to trained workers. American shipyards employed 2 million workers by 1943. Many were completely new to shipbuilding, but they were trained quickly using standardized methods and simple, repetitive tasks. Kaiser's Richmond shipyards alone employed 90,000 workers at peak production. That single shipyard complex had more workers than all three of Japan's major naval shipyards combined. The Richmond workforce looked nothing like traditional shipyard crews. 40% were women, many of whom had never held industrial jobs before. They were farm wives from the Midwest, teachers from rural towns, office workers from cities across America. They learned to weld in 2 weeks of training. They learned to operate cranes in 3 days. They learned to read blueprints in 1 week. Traditional shipbuilders said these inexperienced workers couldn't possibly build quality ships. They lacked the years of apprenticeship required for precision metalwork. But Kaiser's prefabrication system didn't require years of experience. It required workers who could perform one specific task repeatedly and accurately. A welder in the Richmond yards didn't need to understand naval architecture or ship theory. She needed to know how to weld a specific type of seam on a specific type of joint. The blueprints showed her exactly where to weld. Jigs and fixtures held everything in precise position. She moved from one piece to the next, welding identical joints dozens of times per shift. Repetition created expertise faster than traditional apprenticeship. After 1 month, new workers became proficient. After 2 months, they became fast. After 3 months, they could work at speeds that exceeded traditionally trained shipwrights who had spent years learning their trade. The Japanese couldn't replicate this model because they lacked the industrial infrastructure for true mass production. Japanese shipyards employed 300,000 workers total, spread across dozens of projects and facilities. Many were highly skilled craftsmen, but they were spread too thin. Training new workers was slow because experienced workers were too busy with production to teach effectively. More critically, Japanese industrial culture emphasized craftsmanship over standardization. A skilled Japanese ship fitter took pride in custom fitting each piece, making minor adjustments to ensure perfect alignment and fit. That approach produced beautiful ships, but it was devastatingly slow compared to American methods. American workers didn't custom fit anything. Parts were manufactured to precise specifications in prefabrication shops. They either fit together correctly or they were rejected, and new parts were made. That approach produced functional ships rapidly. Speed mattered more than aesthetic perfection in wartime production. The philosophical difference reflected the industrial capacity difference. Japan had limited steel, limited machine tools, limited workers. Every piece had to be used efficiently. Waste was unacceptable. Custom fitting ensured nothing was wasted, even if it slowed production. America had abundant steel, abundant machine tools, abundant workers. If a piece was manufactured incorrectly, they made another one. Speed of production mattered more than elimination of all waste. Both approaches had merit in different contexts, but in total war, speed won decisively. Newport News Shipbuilding developed specialized assembly areas for different carrier components. One building, 500 feet long, was dedicated entirely to fabricating flight deck sections. Giant overhead cranes moved steel plate from storage racks to cutting stations where workers with acetylene torches cut plates to specifications. The cut plates moved to edge preparation stations, where workers beveled edges for welding, then to assembly jigs where plates were aligned and tack welded together. Finally, to welding stations, where teams of welders completed permanent welds, working in carefully coordinated sequence, with each welder responsible for a specific section. A complete flight deck section 100, 20 feet long by 90 feet wide, took 8 days from raw steel to finished component. That same section, built using traditional methods with a single crew working in the slipway, would require 6 weeks. Another building fabricated elevator assemblies. Carrier elevators were extraordinarily complex mechanisms, hydraulically powered and capable of lifting 30-ton aircraft from hangar deck to flight deck in 30 seconds. Traditional shipyards installed elevators piece by piece inside the carrier hull. It was difficult, cramped work requiring precise alignment and extensive testing. Newport News built entire elevator assemblies in a dedicated shop where the complete assembly was tested, adjusted, and verified before it ever reached the ship. When installation time arrived, cranes lifted the complete tested elevator into position. Connection to hydraulic systems took days instead of weeks, and the elevator was guaranteed to work properly because it had been fully tested before installation. Propulsion systems received identical treatment. Each Essex-class carrier needed 4 sets of turbines, 8 boilers, reduction gears, propeller shafts, and thousands of feet of steam piping. Installing this machinery traditionally consumed months of construction time. Newport News created complete propulsion module assemblies. Each module contained 1 complete turbine set, 2 boilers, and all associated piping, pre-assembled and tested in a separate facility. The modules were completely outfitted with instrumentation and controls. They were test-fired using temporary steam connections to verify performance before installation. When the carrier hull was ready, cranes lifted entire propulsion modules into machinery spaces. Workers connected steam lines, electrical cables, and control systems. Complete installation took 3 weeks instead of 3 months. This modular approach extended to everything on Essex-class carriers. Radar systems were pre-assembled and tested as complete units. Entire radar masts with antennas, transmitters, receivers, and power supplies were built in electronics shops, then installed as functioning units. Crew accommodations were prefabricated. Berthing compartments with bunks, lockers, lighting, and ventilation were assembled in specialized shops, then lifted into position in the hull. Even small items were ruthlessly standardized. Every hatch was identical. Every door, every ladder, every ventilation duct, all built to standard specifications that fit standard openings throughout the ship. Workers didn't measure and cut and fit each piece individually. They grabbed pre-made components from storage, bolted or welded them in place, and moved immediately to the next task. The result was carriers that went from keel laying to launch in 6 to 8 months, then spent another 6 to 8 months in outfitting and trials before commissioning. Total time, 14 to 16 months from start to operational carrier ready for combat. Japan couldn't match this because they lacked 3 critical elements that American industry possessed in abundance. First, they lacked the industrial infrastructure for genuine mass production. Prefabrication required factories that could produce thousands of identical components with precision tolerances, measured in thousandths of an inch. American industry had developed that infrastructure through decades of automobile manufacturing, appliance manufacturing, and consumer goods production. American factories were designed around assembly lines, standardized parts, and interchangeable components. Workers understood systematic production. Managers understood logistics and quality control. The entire industrial culture supported mass production. Japanese industry had limited experience with this style of mass production. Most Japanese manufacturing was small-scale and custom work-oriented. Precision parts came from specialized machine shops making small quantities, not assembly lines producing thousands of identical components. Attempting to replicate American prefabrication methods would have required building entirely new factories, training entirely new workforces, and developing entirely new supply chains, from raw materials to finished components. Japan didn't have the time, resources, or expertise for that fundamental industrial transformation. Second, they lacked raw material capacity for wasteful prefabrication methods. Prefabrication is inherently wasteful. You cut more steel than you need. You manufacture parts that don't fit properly and must be scrapped. You overstock components to ensure you never run short and delay construction. When Kaiser's Richmond yards built a Liberty ship, they ordered 15% more steel than the ship theoretically required. The extra steel covered waste, mistakes, rejected parts, and inventory buffers. That approach worked perfectly when steel was abundant. It failed catastrophically when steel was scarce. Japan couldn't afford 15% waste on any project. Every ton of steel plate was precious and had to be used efficiently. Waste had to be minimized through careful planning and custom fitting. That requirement meant slower construction work, which meant longer construction timelines, which meant fewer carriers produced. Third, Japan lacked the transportation infrastructure that made American prefabrication possible. American modular construction worked because components could be manufactured anywhere in the country and shipped to shipyards by rail, within days. A bulkhead section built in Pennsylvania could be loaded on a flatbed rail car to Newport News within 24 hours. 2 days later, it was being welded into a carrier hull. Japan's rail network was severely limited compared to America's continental rail system. Most heavy components moved by coastal shipping between Japanese ports. That shipping was under constant, devastating attack by American submarines. A turbine built in Kobe might take 2 weeks to reach Yokosuka Naval Arsenal by ship, assuming the transport wasn't sunk. If the transport was torpedoed, which happened with increasing frequency, the turbine was lost completely, and a replacement had to be built from scratch, adding months to construction schedules. Supply chain vulnerabilities crippled Japanese naval construction more severely than any other single factor. The Americans faced no such constraints. American shipyards received steel, aluminum, copper, rubber, electronics, everything they needed by rail and truck from factories across the continent. If one supplier had problems, there were alternative suppliers. Competition between suppliers actually improved quality and reduced prices. The supply chain was robust, redundant, and reliable. Japanese shipyards depended entirely on ocean shipping for critical materials. Steel came from mills in Korea and Manchuria. Copper came from mines in the Philippines until those were captured by American forces. Rubber came from plantations in the Dutch East Indies. All materials had to be transported by merchant ships that were being sunk by American submarines at catastrophic rates. By 1944, Japan was losing merchant shipping faster than shipyards could possibly replace vessels. Critical materials weren't arriving on schedule. Construction programs were delayed for months because shipyards were waiting for steel plate, turbine blades, or electrical cable that was sitting at the bottom of the ocean inside torpedoed transports. The logistics crisis forced compromises that degraded carrier capability. Taiho had been designed with 8 boilers and 4 turbines, producing 160,000 shaft horsepower for 33-knot maximum speed. When turbine production fell behind schedule due to material shortages, 2 of the Unryu-class carriers received destroyer engines instead, because that was what was available. Those carriers could only make 25 knots, making them vulnerable in combat. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Americans faced no such compromises. Every Essex-class carrier received identical, full-capability propulsion systems, 150,000 shaft horsepower, 33 knots, no exceptions, no substitutions. When a component wasn't immediately available, they simply pulled one from inventory or expedited production. The supply chain never failed. Beyond construction challenges, Japan faced an even more devastating crisis in pilot training. Building carriers was only half the challenge. Training pilots to fly from them was equally critical, and by 1943, Japan was losing that battle catastrophically. Before the war, Japan had possessed the finest naval aviators in the world. Pilot training required 2 full years before a pilot's first carrier landing. They practiced navigation, gunnery, formation flying, night operations, and carrier approaches until every skill was perfected. Japanese carrier pilots in December 1941 had an average of 800 flight hours and 2 years of intensive training. They were the elite. By 1943, Japan didn't have 2 years for pilot training. They didn't have 1 year. American submarine warfare was destroying Japanese merchant shipping, which meant tankers carrying fuel oil weren't reaching Japan. Less fuel meant shorter training flights. Pilot training programs were shortened from 24 months to 12 months, then to 8 months, then to 6 months, as fuel became increasingly scarce. Pilots were graduating to fleet squadrons with 100 flight hours instead of 800. They could fly basic formations and shoot their weapons, but they lacked the experience to survive combat against veteran American pilots who had 500 to 1,000 combat hours. Saburo Sakai, one of Japan's top aces with 64 confirmed victories, was pulled from combat duty in early 1943 to serve as a flight instructor. He was shocked by what he found. The training program was completely overwhelmed. Instructors had too many students and too little time. Classes were rushed through abbreviated curriculums. Fundamental skills were being skipped entirely because there wasn't time to teach them properly. Sakai later wrote that instructors were explicitly told to rush men through training. Forget the fine points of aerial combat. Just teach them how to fly straight, how to take off and land on carriers, and how to shoot at enemy aircraft. Send them to fleet squadrons, and hope they learn the rest through experience before they're killed. The pilots who graduated from these catastrophically abbreviated programs were sent to carrier squadrons to fill out depleted air groups. They were brave, dedicated, and absolutely willing to die for their country. But they weren't ready for combat against experienced American aviators flying superior aircraft. At the Battle of the Philippine Sea in June 1944, the consequences of this training crisis became devastatingly apparent. Japan committed 9 carriers to the battle. 3 fleet carriers, Taiho, Shokaku, and Zuikaku, plus 6 light carriers. Those 9 carriers embarked 450 aircraft total. That was less than half the aircraft capacity those carriers were designed to carry. Japan simply didn't have enough trained pilots and serviceable aircraft to fully equip its carriers. Worse, the pilots flying those aircraft were inadequately trained by any reasonable standard. The average Japanese carrier pilot at Philippine Sea had completed 6 months of training and had 20 hours of combat flight time. Some had no combat experience whatsoever. They were flying their first carrier operation against the largest, most experienced naval aviation force ever assembled. American Task Force 58, commanded by Admiral Mark Mitcher, fielded 15 carriers, 7 Essex-class fleet carriers, and 8 light carriers. Those carriers embarked 956 aircraft, more than twice the Japanese total. Every American aircraft was superior to its Japanese counterpart in critical performance categories. The F-6F Hellcat fighter had a maximum speed of 380 miles per hour compared to the A-6M0's 340 miles per hour. The Hellcat could dive at 450 miles per hour without structural failure. The Zero's maximum dive speed was 360 miles per hour before structural damage occurred. The Hellcat was heavily armored with pilot armor, self-sealing fuel tanks, and armored engine cowling. It could absorb tremendous battle damage and continue flying. The Zero had no armor protection whatsoever. A single burst of machine gun fire through an unprotected fuel tank would ignite it instantly. Pilot casualties were catastrophic because they had no protection from gunfire. The Hellcat mounted 650 caliber machine guns with combined firepower of 1,800 rounds per minute. The Zero mounted 2 20mm cannons and 2 7.7mm machine guns, respectable armament, but less sustained firepower than the Hellcat's 6 heavy machine guns. Most critically, American pilots in June 1944 were combat veterans. The average American fighter pilot in Task Force 58 had 200 hours of combat flight time. Many had 300 hours or more. They had fought at Tarawa, Truk, Hollandia, and dozens of smaller engagements. They knew their aircraft's capabilities intimately. They knew how to exploit the Hellcat's advantages. They knew how to fight Zeros and win consistently. The result was entirely predictable to anyone who understood these disparities. On June 19th, Japan launched its first strike wave at 7:30 in the morning. 69 aircraft headed toward the American carriers. American radar detected them at 150 miles range. Fighter directors vectored 40 Hellcats to intercept. The Hellcats hit the Japanese formation 40 miles from the carriers before the strike could reach attack range. They shot down 42 aircraft in the first 10 minutes of combat. The Japanese formation simply disintegrated under the assault. The surviving Japanese aircraft continued toward the carriers, desperately trying to complete their mission. They encountered a second wave of American fighters, then a third wave, then devastating anti-aircraft fire from screening destroyers and cruisers. 8 aircraft finally broke through all the defenses and reached the carriers. They scored no hits. 4 aircraft returned to their carriers. Japan's first strike lost 94% of its aircraft for 0 damage inflicted. The second strike, launched at 8:56 in the morning, fared no better. 109 aircraft met the same layered defense. American fighters destroyed 97 of them before they reached attack range. The few survivors achieved nothing. The third strike, 107 aircraft, achieved a single bomb hit on the battleship South Dakota, causing minor damage that was repaired within days. The fourth strike became completely disoriented. Some aircraft found American carriers but were driven off without attacking. Others never located the enemy at all and returned to their carriers with bombs still attached, having accomplished nothing. Of 450 aircraft launched, 300 were shot down in combat. Another 50 crashed, attempting to land on carriers in darkness after the battle. Japan lost 350 aircraft and their irreplaceable pilots in one day of combat. America lost 29 aircraft. That exchange ratio, 12-1 in America's favor, reflected the cumulative advantages of superior aircraft, superior pilots flying those aircraft, superior doctrine coordinating the defense, and superior radar providing early warning and fighter direction. It also reflected the consequences of Japan's failed carrier construction program. If Japan had been able to build carriers as fast as America, they could have deployed 20 or 30 carriers to Philippine Sea instead of 9. Even with inferior pilots and inferior aircraft, 30 carriers would have deployed over 1,000 aircraft. Sheer numbers might have overwhelmed American defenses through saturation. But Japan had only 9 carriers, and by the end of the battle, 3 of them were gone. Taiho survived just 3 months after commissioning. She was hit by a single torpedo from the American submarine Kavala on June 19th. The damage should have been manageable. Japanese damage control doctrine was adequate for single torpedo hits, but a young, inexperienced damage control officer made a catastrophic error. He ordered the ship's ventilation system turned on to clear gasoline fumes from the hangar deck where damaged aircraft were leaking fuel. The ventilation system spread the fumes throughout the ship instead of venting them overboard. 6 hours after the torpedo hit, a spark from unknown source ignited the gasoline vapor that had accumulated throughout interior spaces. The explosion tore the ship apart from the inside. She sank in minutes, taking 1,272 men with her. 32 months to build, 3 months in service, destroyed by a single torpedo and a ventilation system error. Shokaku, one of Japan's most successful carriers and veteran of Pearl Harbor, Coral Sea, and Santa Cruz, was hit by 4 torpedoes from the submarine Kavala during the same battle. She sank 7 hours later, her experienced crew unable to contain the flooding. Hio was hit by aerial torpedoes and bombs. She caught fire, lost power, and sank. Japan lost 3 carriers in one day. The Americans lost none. Their superior damage control, better training, and more robust ship design kept every American carrier operational despite taking damage. By late 1944, Japan's carrier force was effectively finished as a combat-capable force. At the Battle of Leyte Gulf in October, the Japanese committed their 4 remaining carriers as a pure decoy force. 4 carriers with almost no aircraft embarked sailed north to draw American carriers away from the main battle area where Japanese battleships would attack the invasion fleet. The plan worked, tactically. American carrier aircraft attacked the decoy force and sank all 4 carriers. But the sacrifice achieved nothing strategically. American escort carriers in Leyte Gulf fought off the Japanese surface fleet anyway using the few aircraft they had. The decoy operation cost Japan its last carriers for 0 strategic gain. Zuikaku, the last survivor of the 6 carriers that had attacked Pearl Harbor, went down on October 25, 1944. She had survived 3 years of combat operations. She was sunk not because of American tactical superiority, but because Japan no longer had enough aircraft or trained pilots to defend her properly. By November 1944, Japan had no operational fleet carriers remaining. America had 28 Essex and Independence-class carriers operating in the Pacific. The disparity was absolute and irreversible. The American industrial advantage wasn't just about numbers. It was systematic superiority in every aspect of carrier operations. When an Essex-class carrier was damaged in combat, it sailed to a naval yard for repairs. The repairs were completed in weeks or months, using prefabricated replacement sections, standardized parts, and massive repair facilities with thousands of skilled workers. USS Franklin was hit by 2 bombs on March 19, 1945, while operating off the Japanese coast. The bombs penetrated the flight deck and exploded in the hangar bay, triggering massive secondary explosions from fueled and armed aircraft waiting to launch. Fires raged for hours. 724 men were killed. The ship was dead in the water, listing heavily, burning uncontrollably with magazines threatening to explode. Any other navy would have abandoned ship. Franklin was clearly a total loss by traditional standards. But American damage control teams fought the fires with techniques learned in specialized schools. They stabilized the list using counter-flooding. They got emergency steam to the engines. Franklin sailed to Pearl Harbor under her own power at 14 knots, a floating wreck that refused to sink. From Pearl Harbor, she transited to Brooklyn Navy Yard for complete repairs. The ship arrived at Brooklyn on April 28, 1945. The war ended before she could return to combat service, but she survived damage that would have sunk any Japanese carrier instantly. That level of damage control capability was simply impossible for Japan. Japanese carriers hit by major attacks usually sank quickly or had to be scuttled. Japan lacked the repair facilities, the replacement parts, the trained damage control personnel, and the industrial capacity to save heavily damaged ships. By 1945, the Japanese Navy had effectively ceased to exist as a fighting force capable of contesting American control of the Pacific. Japan still possessed some battleships, cruisers, and destroyers, but without carriers to provide air cover, those ships couldn't operate in areas where American carrier aircraft could reach them, which was essentially everywhere in the Pacific. American carrier strikes in July 1945 ranged freely over Japan itself, hitting airfields, factories, ports, and naval bases. Japanese air defenses were completely overwhelmed. Japanese fighters were outnumbered 20-1 or 30-1. Fuel shortages meant defensive fighters often couldn't even take off to intercept incoming strikes. The final accounting was devastating for Japan. They had commissioned 6 new carriers during the entire war, 3 Unryu-class fleet carriers and 3 converted light carriers. America had commissioned 24 Essex-class fleet carriers, 9 Independence-class light carriers, and over 100 escort carriers. The final ratio was roughly 20 American carriers built for every Japanese carrier completed during the war. That 20-1 production ratio told the complete story of how industrial capacity determined the outcome of the Pacific War far more decisively than any battle, any admiral's tactical genius, or any technological innovation. Japan had entered the war with the finest carrier force in the world, built over 20 years by the most experienced naval architects and shipbuilders in Asia. They had the best pilots, the best operational doctrine, and 20 years of carrier experience. America entered the war with an untested carrier force and had to learn carrier operations essentially from scratch. But America possessed something Japan could never match: industrial capacity operating at scales that seemed physically impossible to Japanese planners. Raw materials in unlimited quantities. Technological innovation applied systematically to production problems. The ability to learn from mistakes, adapt quickly, and scale production to levels that defied belief. Vice Admiral Ozawa, standing on Taiho's bridge in March 1944, had known the numbers even then. He knew Japan had already lost the war. The shooting would continue for another 16 months. Tens of thousands more would die. But the outcome was decided by mathematics, by steel production, by welding techniques, by assembly line methods perfected in automobile factories and applied to shipbuilding with devastating effectiveness. The lessons from the carrier construction race extended far beyond World War II. Industrial capacity matters more than tactical brilliance or individual courage. Japan had superior carrier doctrine in 1941, better pilots, better aircraft, better operational experience. They won every battle for the first 6 months of the war. But tactical advantages erode over time. Pilots die and must be replaced. Aircraft become obsolete as technology advances. Doctrine evolves as opponents adapt. Industrial advantages compound exponentially. Every new carrier America built made it easier to build the next one using lessons learned. Every trained worker made training the next worker faster and more efficient. Every standardized component made the supply chain more reliable and responsive. By mid-1943, American carrier construction had become a self-reinforcing system, operating with mechanical efficiency. Shipyards were completing carriers faster than the Navy could train complete crews for them. The bottleneck wasn't construction, it was crew training, and even that was being solved through systematic approaches. Japan never achieved that momentum. Every carrier they built consumed resources desperately needed for the next one. Every worker trained took time away from production. Every component standardized required retooling factories that were already overloaded with other urgent projects. The gap widened exponentially rather than linearly. In early 1942, Japan had 8 operational carriers, and America had 3. By mid-1943, Japan had 6 operational carriers. America had 14. By mid-1944, Japan had 7 operational carriers, and America had 32. By early 1945, Japan had 0 operational carriers, and America had 39 fleet and light carriers, plus over 100 escort carriers. The progression wasn't arithmetic, it was geometric. American strength doubled, then tripled, then quadrupled, while Japanese strength declined absolutely. That pattern repeated across every category of naval construction and revealed the true nature of industrial warfare. The Pacific War was decided in shipyards long before it was decided in battles. Battles determined when the war would end and how many would die before surrender. But shipyards determined who would win with absolute certainty. American shipyards, with their prefabrication techniques, their welding innovations, their standardized designs, and their armies of workers who had never built ships before the war, crushed Japan's naval power through sheer industrial output operating at unprecedented scales. Admiral Yamamoto had warned Japan's leaders before Pearl Harbor. He said Japan might win battles for 6 months, perhaps a year. After that, American industrial power would bury them under a tide of ships, aircraft, and munitions they could never hope to match. He was exactly correct. But even Yamamoto, who understood America better than any Japanese leader, underestimated how quickly American industry would mobilize and how completely it would dominate production. He thought it would take America 2 years to replace losses from Pearl Harbor and early battles. It took 9 months. He thought American carrier production might peak at 8 to 10 carriers annually. America produced 18 carriers in 1943 alone. Every assumption Japanese planners made about American industrial capacity was wrong. Every assumption underestimated America's ability to mobilize resources, train workers who had never done industrial work, and produce weapons at scales Japan couldn't imagine even when confronted with evidence. The story of carrier production in World War II remains relevant today for anyone studying warfare, strategy, or international competition. Wars between industrial powers are won in factories long before they're decided on battlefields. The side that can produce more weapons, train more personnel, and sustain operations longer will win regardless of tactical skill or individual courage. Japan learned this lesson at catastrophic cost. They entered the war believing spirit could overcome material disadvantage. They believed their superior warrior culture and tactical excellence could defeat American industrial capacity. They were completely, utterly wrong, and 400,000 Japanese sailors and airmen died learning that terrible truth. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.